So I'd ask you to balance it, and then I would ask you to determine the oxidation number of each element in each compound on both sides of the reaction. Because the way to determine if it's a reduction or an oxidation is to look at see how the oxidation number for an element changes from the reactant side to the product side. So to balance it, I've got 3 hydrogens on the right and only 1 on the left, so maybe I'll put a 3 here. It gives me 3 hydrogens now on both sides. I've got 3 nitrogens on the left and only 2 on the right. So I probably want to change this number so I'm not disturbing the number of hydrogens. Now I've got 6 oxygens on the left and 6 on the right, and everything's balanced out. So I've got the reaction balanced. Now I want to determine the oxidation numbers. I really don't need to have it balanced to determine the oxidation numbers. So even if you have trouble balancing this, you can still get the oxidation numbers for the elements. So when there's no metals involved, to determine the oxidation numbers, usually I want to draw the Lewis structures if I can. So for HNO2, I put the nitrogen in the middle, put the oxygens here, and then I have a question, do I want to put the hydrogen on the nitrogen or do I want to put it on the oxygen? This is actually one of the ones a lot of you did in the lab, and what you found was if you put the hydrogen on the nitrogen, you can't minimize the formal charge. You can't draw a structure with no formal charge. So if you found that, you would then put it on the oxygen so that when you put the remaining valence electrons in, there will be 1 plus 5 plus 12. 18 total valence electrons. I've used 6 so far. I need 12 more. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Putting them on the more electronegative atoms first. Then I would want to share from here to avoid the formal charge and to complete the noble gas configuration for the nitrogen. Then to determine, well actually let's just draw the other Lewis structures real quick. So for HNO3 I would do the same thing, but now I've got 3 oxygens. And again I need the hydrogen on the oxygen to make sure that I have the least amount of formal charge as possible. Put the valence electrons in. Counting them up, I would find out I have that many. Then the nitrogen still needs more electrons, so I've really got 2 good options. I'm not going to share electrons from the oxygen with the hydrogen on it because it's going to create unnecessary formal charge. I'm going to share from either one of these other 2 oxygens, and that's going to mean that I have resonance because both oxygens can shift electrons in there to the nitrogen. But I really only need to look at one of the resonance structures to look at oxidation numbers. So then I've got water and NO, which will have 5 valence electrons plus 6. So this has 11 valence electrons, which is weird to have an odd number of valence electrons, but the structure we come up with has to have that number. There's no charge shown on the molecule, so it doesn't have an even number of valence electrons. So I've used 2 out of the 11. I've got 9 left. 1, 2, 3, 4, 5, 6, 7, 8, 9. Since the oxygen is more electronegative, it's going to have the electrons attracted to it more than the nitrogen. So if I have a deficiency of electrons, it's going to be on the nitrogen. Then the nitrogen can use a couple more, so I'll share those in there. So the nitrogen, with an odd number of electrons, I'm never going to be able to complete all the noble gas configurations. So as soon as I see I have an odd number, I know that I'm not going to make a noble gas configuration. One of these atoms is not going to have enough electrons. It's going to be the nitrogen because it's not as electronegative. It doesn't attract the electrons as well. So that's the best Lewis structure I can make for that. At least there's no formal charge, even though I don't have a complete octet on the nitrogen. So now I've got the Lewis structures drawn. I need to analyze To get the oxidation numbers, I make a similar analysis to calculating formal charge, but for the oxidation numbers, I'm not going to split the shared electrons up evenly like I would for formal charge. I'm going to allow the more electronegative atom to draw the electrons toward it. So since oxygen is more electronegative than nitrogen, which is more electronegative than hydrogen, I know that the oxygen is going to be drawing all the electrons to itself. And that's true unless the oxygen's bonded to another oxygen, which they would be split evenly, or if the oxygen's bonded to a fluorine, which is the only element more electronegative than it, in which case the fluorine would draw the electron. But in this case, the oxygen's my most electronegative. So if I redraw this, I'm going to take all the shared electrons and put them on the oxygen. And then lone pairs obviously are not going to be moved from one atom to another. They're on that atom. But this oxygen here is also going to be drawing all the shared electrons to it. So now I've assigned the electrons. I'm assigning them differently from how I do with formal charge. But the formal charge formula is then going to apply for me to calculate oxidation numbers. So the formal charge for oxygen in both of these oxygens in this molecule is 6 minus the 8 that it has assigned to it, which is a -2. So the oxygen oxidation number here is minus 2. It's not its charge, it's its oxidation number. The nitrogen here, which is in 5A, normally would have 5 electrons, but I can only assign 2 to it because the oxygen are pulling all the other ones away. That gives it a +3. That's its oxidation number. And the hydrogen, which is almost always lower in electronegativity than whatever it's sharing electrons with, it's almost always going to have its electrons pulled away by the more electronegative element. When we're calculating oxidation numbers, it's almost always going to be 1 minus 0. So the hydrogen then is a +1. Looking at the products, I would do the same thing. I would draw here the molecule and recognize that the shared electrons are going to be pulled more toward the more electronegative atom. And again, all the oxygens in this case have 8 electrons assigned to them, so 6 minus 8 is going to be a -2. But the nitrogen now doesn't have any electrons assigned to it, so the nitrogen is 5 minus 0, which is +5. So the nitrogen's oxidation number is changing. The hydrogen still has 0 electrons assigned to it, so it's still +1. In water, the oxygen's pulling the electrons away from the hydrogen, so it has 8 assigned to it. 6 minus 8 gives me a -2. And each hydrogen has 0 electrons assigned to it, so 1 minus 0 gives me a +1. And then the final product, the oxygen's more electronegative. As we said, these oxygens in this reaction are all attached to less electronegative atoms. So they're all pulling all the electrons toward themselves. That means they're always going to have 8 assigned. So the nitrogen here will have 3 assigned to it. So the oxygen is going to be 6 minus 8, as it was in every other example in this reaction. But the nitrogen is going to be 5 minus 3 because it has 3 assigned, so it's a +2. And so that gives it a +2. So that's how you calculate the oxidation numbers. And then I would probably ask you to determine which element is being oxidized and which is being reduced. So again, when you calculate the oxidation numbers, it's not for a compound. A compound doesn't have an oxidation number for it. The elements in the compound have oxidation numbers. So it's the elements that are either being oxidized or reduced by increasing their oxidation number or decreasing it. So what I have here is the oxygens and hydrogens have the same oxidation number in every compound here. There's no change. So the oxygens and hydrogens are not undergoing any reduction or oxidation. What is changing is that in some of my nitrogens, they're going from a +3 to a +5. So some of the nitrogens are being oxidized. But some of the nitrogens are going from a +3 to a +2. And that's a decrease in the oxidation number. That's a reduction. So the nitrogen is both oxidized for some of the nitrogen atoms, and for other nitrogen atoms in the reaction, they're being reduced. In fact, oops, that didn't work. Try that again. Two of the nitrogens are being reduced, and one of the nitrogens of the three that I'm starting with is being oxidized. Questions about that? You can't have an oxidation without a reduction. If somehow you calculated these numbers and you found that for some of the elements on the reactant side their oxidation numbers were going up, but you didn't calculate any oxidation numbers going down, that's not possible. So that's another way to kind of check what you've done and at least have an idea that it might be correct. You guys want to look at another example like that, or do you want to move on to something else? Mike? Yeah, so the way to know for sure is to look to see what change occurs for an element's oxidation number in a reaction. Right? So if I calculated that, like let's look at a different reaction real quick, just to contrast with this one. If I calculated that I had something like this, and I'm going to make H3O plus and NO2 minus. In this reaction, down here, I'd go through the same process. I would draw the Lewis structures, I would see how the electrons are pulled to the more electronegative atom, I would use that to assign the electrons and calculate the oxidation numbers using the formal charge formula. I would find that the hydrogens are all at a +1, the oxygens are all at a -2, and in this case the nitrogens are all at a +3. So none of the elements' oxidation numbers are changing, which means this is not a redox reaction. It's not an oxidation-reduction reaction. There's no oxidation occurring, there's no reduction occurring. So ultimately, the way to judge what's being oxidized and what's being reduced is to calculate those oxidation numbers for each element on both sides of the reaction, and then to see, are they changing? If they're not changing, it's not a redox reaction. If they're changing, then whichever element is specifically going up in its oxidation number, so from +3 to +5, that element is being oxidized. And then that's what makes an oxidation, is an increase in the oxidation number. If an element's going down from a +3 to a +2, then that element is being reduced. So the oil rig mnemonic is used by a lot of people. Oil rig, oil meaning oxidation is loss, rig meaning reduction is gain. That's if you put it in terms of whether electrons are being lost or gained. But it's counterintuitive, because a reduction doesn't mean something's going up or being gained. It means something's going down. So if you know what the word reduction means, or some reduce means you're losing something, something is taken away, think of it in terms of the oxidation number, you'll get it right. Because a reduction means you have a decrease or a reduction in the oxidation number for some element. The element that's being reduced has its oxidation number going down or being reduced. Questions about that? All right, I want to do just one more of these because I want to show you an example of what the analysis is slightly different if you have a metal involved. So, let's see if I can find a good one here. Let's look at 117J. So here we have FeCl2 and Cl2 producing 2 FeCl3. So I've got 2 irons on both sides and 6 chlorines on both sides, so that should be balanced. So the last example we saw, all of the elements were nonmetals, and when they're sharing electrons, you really need to draw the Lewis structures, have the more electronegative atom pull the electrons, and then use that to assign the electrons and calculate the oxidation numbers like we did. When there's a metal involved, it's usually much more straightforward. If you can determine the charge on the metal, that will be its oxidation number. Or if you have a nonmetal atom that has a charge, that will be its oxidation number. And when metals and nonmetals combine together, they combine together with charges. Usually either the metal and the nonmetal, or one or the other, will have the number of electrons they need to make a noble gas configuration, and whatever charge that gives to the metal or nonmetal, that will be its oxidation number. So if I'm combining iron and chlorine, how can I figure out what charges they have? Right. So I would look to see for the metal or for the nonmetal or for both how many electrons they need to lose or gain to make their octet or their noble gas configuration. For iron, it's hard to tell because the iron isn't close to a noble gas. So the charge on the iron, I would not expect you to predict if that was all I said was, here's an iron atom and it's going to be charged, what's its charge going to be? You can't answer that because it could have different charges depending on what oxidation state it's in. But for chlorine, if chlorine joins with a metal, it has to have a charge to attract to the metal, and for chlorine to have a charge, it's 1 away from noble gas, so it's always going to have a -1 charge. So if the chlorine has a -1 charge, that means its oxidation number is -1. So over here, I see the chlorine's joined with the metal. It also, if it's joined with the metal, will have a charge to attract to the metal's positive charge. And since chlorine's 1 away from a noble gas configuration, it needs to have a -1 charge and a -1 oxidation number. So even though I can't usually predict offhand what the charge on the iron would be, if it's combined with a nonmetal whose charge I can't predict, I can then deduce the charge on the metal, recognizing that the overall combined formula for the metal and the nonmetal has to be neutral or have a 0 charge overall. So if I have 2 Cl minuses, what must be the charge on the Fe? It must be a 2 plus. The charge has to be balanced if it's creating a neutral unit. So the iron's oxidation number is a 2 plus. If I have an iron combining with 3 Cl minuses, then its charge must be 3 plus, and its oxidation number must be 3 plus. Questions about that? With the Cl2 though, the Cl2 is not involving a metal. So I can't necessarily predict what its charge would be. I'd have to look at its Lewis structure, which is straightforward. If I've got two chlorines, they have to be sharing electrons. If they're both nonmetals, which they are, so there's no metal involved, my nonmetals are going to share to make their noble gas configurations. And I've got 14 total valence electrons, so I'd put those in. So then, in this case, since the elements sharing have the same electronegativity, when I assign the electrons, I have to split them up evenly. Normally, for oxidation numbers, the more electronegative atom is going to pull the electrons, and I would assign all the shared electrons to the more electronegative atom. But in this case, they have the same electronegativity. So if I'm assigning electrons, I would assign them evenly to both atoms. And since chlorine is in 7A, and there are 7 electrons assigned, its oxidation number is 0. So what is being reduced here? The chlorine. Some of, not this chlorine, it's not changing its oxidation state. It's these chlorines. They're changing their oxidation number from 0 to -1. That's a decrease. Going from 0 to -1 is a decrease, so that's a reduction. The chlorine of the Cl2 is being reduced. And what's being oxidized? The iron. It's going from a +2 to a +3. That's an increase in its oxidation number. That's an oxidation. So the iron is oxidized. The Cl of the Cl2 is reduced. Can't have one without the other.